Welcome to episode 2 of the Zephyr RTOS Deep Dive series. In this episode, we move from theory to practice. We will set up the complete Zephyr RTOS development environment on Linux and build our very first Zephyr application, Hello World. If you are new to Zephyr, don't worry. We will go step by step. Before we dive into the command and setup, let's take the step back and look at the bigger picture of this series. This Zephyr RTOS Deep Dive is designed as a structured journey, not a collection of the random videos. In episode 1, we focus on understanding what Zephyr RTOS is, why it exists, and where it is used in the real-world system. That gives us the foundation. Now in episode 2, we move into the most important step, getting a working development environment on your system. This is where Zephyr goes from theory to something you can actually build and run. As we move forward in the series, we will cover Windows setup, threading and scheduling, device driver and real-time behavior. Each episode builds on the previous one, so think of this as a continuous learning path. Now, an important clarification before we continue. This episode focuses only on Linux, especially Ubuntu or Debian-based distribution. All the commands you will see in this video are Linux commands. If you are using Windows, don't worry. The complete Windows setup will be covered in the very next episode. I am intentionally separating Linux and Windows setups so that we don't mix commands or path and cause confusion. The workflow you will learn here is exactly the same on Windows, only the commands and tool changes. So even if you are on Windows, I recommend watching this episode to understand the overall Zephyr workflow and then follow the next episode step by step. Before we start running commands, let's quickly align to what you will gain from this episode. By the end of this video, you will have the fully working Zephyr RTOS development environment on Linux. You will be able to install all the required tools using a single consolidated command. Install and use the best tool to manage Zephyr project and configure the Zephyr SDK. Most importantly, you won't just set things up, you will build and run your first Zephyr application on QEMU and also on real hardware STM32 discovery board. To get there, we will follow a very simple and structured workflow. We will start by installing Linux dependencies. After that, we will set up West, create a Zephyr workspace, then move on to the Zephyr SDK and finally build and run the application. This workflow is the standard Zephyr development flow. Once you understand it, everything else in Zephyr, thread, driver, and real-time behavior will build on top of this foundation. This workflow is designed to scale clearly from small demos to large production systems. Before we start typing commands, let's pause for a moment and understand what this slide is telling us. This slide covers the core tooling and system preparation required for Zephyr RTOS development on Linux. It relies on a small ecosystem of a tool that works together during development. Python is used extensively for Zephyr scripts and tooling. Git is used to download and manage the Zephyr source code and its module. CMake generates the build configuration and Ninja executes build efficiently. You will also see development libraries and cross-compiler listed here. These are critical because Zephyr applications run on embedded microcontrollers, not on your PC. So the firmware must be built using cross-compilers that target the embedded architecture. The key idea of this slide is simple. Instead of installing these tools one by one, we will install everything in one clean step using a single Linux command. Once these tools are installed, the rest of Zephyr setup becomes much easier. Now, before we install everything, let's quickly verify a few important prerequisites. First, make sure you have administrator or sudo access. because we will be installing system level packages. You can verify this by running the command sudo -v in the terminal. If you are prompted for a password and don't see any error, sudo access is available. Next, ensure you have a stable internet connection since Zephyr setup requires downloading multiple tools and repositories. A simple ping or a quick access check to GitHub is enough to confirm connectivity. Ping -c 3google.com. Now confirm that you are running a supported operating system. In this episode, we are using Linux, especially Ubuntu. lsb_release -a, or you can use cat/etc/os-release. Finally, make sure you have at least 5 to 8 gigabytes of free disk space available. This ensures that the SDK, dependencies, and build artifact install without issues. df-h/. First, we update the package index to make sure we install the latest available packages. Now we run a single consolidated command to install all the core Zephyr dependencies. This installs Git, Python development libraries, CMake, Ninja, development utilities, and cross compilers. We are using the no install recommends option to keep the setup minimal and clean. Avoid unnecessary packages. Once the installation completes, let's quickly verify that some key tools are installed correctly. If these commands return version numbers without error, the core tooling setup is successful. At this point, our Linux system is fully prepared with all the core tools required for Zephyr RTOS development. Next, we will install West, Zephyr Meta tool, which we will use to manage the workspace and install the Zephyr SDK. Let's move on to that. Before we install any Zephyr specific Python tools, there's one important best practice we need to follow: creating a Python virtual environment. Zephyr uses Python extensively for its tooling, including the West Meta tool and several build scripts. If we install this tool directly into the system Python, we can easily run into version conflict or permission issues, especially if we work on multiple projects. A Python virtual environment allows us to isolate all Zephyr related Python packages from the rest of the system. We will create this virtual environment inside our Zephyr workspace so everything related to Zephyr stay in one place. Now let's switch to terminal and create the virtual environment. Navigate to Zephyr workspace. First I am navigating to the root directory of the Zephyr workspace. Python 3 -m venv.venv. This command creates a Python virtual environment named .venv inside the Zephyr workspace. The .venv directory contains its own Python interpreter and package manager. Next, we activate the virtual environment. Source .venv/bin/activate. Once activated, you will notice the terminal prompt changes, indicating that we are now using the virtual environment. We can also verify that Python is coming from the virtual environment by checking its path. From this point onward, all Zephyr related Python tools, including Vest, will be installed inside this virtual environment. This keeps the setup clean, avoids system-wide changes, and makes it easy to recreate or remove the environment if needed. If you ever want to exit the virtual environment, you can simply run the deactivate command. At this point, the Python virtual environment is ready. Next, we will install Vest, Zephyr's meta tool, inside this virtual environment and continue with the Zephyr setup. Now that our system is prepared with all the core tooling, the next important piece in the Zephyr ecosystem is tool called Vest. Vest is Zephyr official meta tool. It acts as a single command line interface that understands how Zephyr projects are structured and how all the pieces fit together. Vest is responsible for managing the Zephyr workspace, handling multiple repositories and modules, building applications, flashing binaries to hardware, and even installing the Zephyr SDK. We will be using commands like a Vest init, Vest build, and Vest SDK install. Vest must be installed before anything else in Zephyr workflow. Think of Vest as a project manager for Zephyr. Without it, we would not have a clean or consistent way to work with Zephyr project. The important thing to note here is that we install Vest inside the Python virtual environment, not globally. This keeps all the Zephyr related Python tool isolated and avoid conflicts with the system Python installation. Now that we understand what Vest is and why it is required, let's install it. I am switching to the terminal now. Tip: install Vest. With the virtual environment active, we install Vest using pip. Vest --version. We verify the installation by checking the Vest version. If this command works, Vest is ready to use. At this point, Vest is installed inside our virtual environment and ready to manage the Zephyr workspace. Next, we will use Vest to create the Zephyr workspace. It's important to pause here and understand the order of operation. We install Vest before the Zephyr SDK because Vest is a tool that manages the Zephyr workspace and provides the command we will use to install the SDK. In the next step, We will use Vest to initialize the workspace and install the Zephyr SDK using Vest SDK install command. This ordering keeps the setup clean, consistent, and aligned with the official Zephyr documentation. Now that we have our Python virtual environment set up and Vest installed inside it, the next major step in the Zephyr workflow is creating the Zephyr workspace. The Zephyr workspace is a structured directory that contains the Zephyr kernel, required module, and your applications, all managed by Vest. Zephyr is a modular project, and the workspace is how Vest keeps all the repositories and components in sync. All workspace-related commands are run with the Python virtual environment activated, ensuring Vest uses the correct Python environment. Now let's switch to the terminal and initialize the Zephyr workspace. First, I navigate to the Zephyr project directory and activate the Python virtual environment. The Vest init command initialize the workspace and prepare Vest to manage the Zephyr repositories. Vest update. Next, we run Vest update, which download the Zephyr kernel and all required modules defined by the project. Once the repositories are downloaded, we run Vest Zephyr export. This command configures environment variables so the build system can locate the Zephyr source tree. This command reads the Zephyr project requirements and install all necessary packages and their correct version using pip. Important clarification about SDK order. Before we move on to installing the Zephyr SDK, there is one important clarification about the order we are following. The Zephyr SDK itself does not depend on workspace and can be installed independently. However, since we are using Vest SDK install, which is workspace aware, we first initialize the Zephyr workspace. This allows Vest to install an SDK that matches the Zephyr version you are using and keeps everything consistent. This is the recommended and safest approach, especially for beginners. With the workspace ready, we are now set up to install the Zephyr SDK using Vest. Let's move on to that next. Now that we have installed all the required system dependencies, install the Vest tool and initialize our Zephyr workspace, the next critical step is setting up the Zephyr SDK. Before we install it, let's understand why the Zephyr SDK is needed. Zephyr applications do not run on your PC. They run on embedded microcontrollers. That means we need cross-compiler that can generate firmware for architectures like ARM, RISC-V, and x86. The Zephyr SDK provides these cross-compilers along with debugging tools, ensuring that builds are consistent, reproducible, and reliable across different systems. Instead of manually downloading and installing the SDK, Zephyr provides a much cleaner and recommended approach using the best tool. Now let's switch to the terminal and install the Zephyr SDK. First, I navigate to the Zephyr project directory and activate the Python virtual environment. You should see .venv in the terminal prompt, confirming that the virtual environment is active. Next, I change into the Zephyr source directory. Now we run west SDK install. This single command automatically downloads and installs the correct Zephyr SDK for our setup. The installation may take a few minutes depending on your internet speed. Once the installation completes, we verify it using the west SDK list command. At this point, the Zephyr SDK is installed and aligned with our workspace. Because we used west to install the SDK, Zephyr can automatically detect and use it during builds. We now have everything required to build and run our first Zephyr application. Understanding Zephyr folder structure. Before we write or build any application, it's important to understand the Zephyr folder structure. Zephyr is a large and modular project, and its directory structure reflects how the RTOS is organized internally. In this slide, I am highlighting only the most important directory that you will encounter as a Zephyr developer. Let's start with the port directory. The port folders contain definitions for all supported hardware ports. Each port has configuration file that describes the CPU, memory layout, and peripherals. Next is the kernel directory. This is the heart of Zephyr. It contains the RTOS core, scheduling, threads, synchronization primitive, and timing. As an application developer, you typically do not modify the kernel directly. The drivers directory contain hardware drivers for peripherals like the GPIO, UART, SPI, I2C, and sensors. This drivers provides hardware-independent API, which allows the same application code to run on different ports. The subsys directory contain higher level subsystems such as networking, Bluetooth, file system, and power management. You will often use these subsystems but rarely need to modify them directly. Finally, the samples directory contains example applications. This is one of the most important directories for beginners. Samples demonstrate how to use different Zephyr features and are the best place to start learning. A useful way to think about this structure is the kernel, drivers, and subsystems form a Zephyr platform. Your application code lives outside these directories. As an application developer, you usually write code in your own application directory or starts from samples rather than modifying Zephyr internals. Over time, you will become familiar with directories you interact with regularly and which one you simply rely on. Understanding this folder structure helps you to navigate the Zephyr confidently and avoid accidental changes to core components. Now that we know where things live, we are ready to look at our first Zephyr application, which is located in the sample directory. Let's move on to the next. Now that we understand the Zephyr folder structure and have the SDK installed, it's time to build and run our first Zephyr application. We will start with the classic Hello World sample, which is used to verify that the entire Zephyr development environment is working correctly. In this slide, I will show you how to run the same application in two ways. First using QEMU and then on real hardware using the STM32 F429i discovery board. The Hello World sample is located inside the sample/Hello World directory. It contains main.c file that prints a message using print key when the system starts. If this application built and runs successfully, it confirms that our toolchain, SDK, and workspace are set up correctly. Now let's build the application. First, I navigate to the Zephyr source directory and make sure the Python virtual environment is active. Let's start with QEMU, which allows us to run Zephyr application without any physical hardware. Here QEMU_x86 specifies the emulated board and sample/hello world is application we are building. Once the build complete, we run the application using QEMU. If everything is working correctly, you should see the Hello World message printed in the terminal. Now let's do the same thing on real hardware using the STM32 F429i discovery board. Make sure the board is connected through USB and the required debug drivers are installed. This time we built the application for the STM32 F429i discovery board. Once the build is complete, we flash the application to the board using best flash command. After flashing, the board reset and run the application. You should see the Hello World's output on the board's console or debug output. The important takeaway here is that the same Zephyr application can run on both an emulator and real hardware simply by changing the board target. This is one of the key strengths of Zephyr, portability across platforms. At this point, you have successfully built and run your first Zephyr application on Linux. You have seen it running in QEMU and on real STM32 hardware. This completes the Linux setup flow. In the next slides, we will quickly go over useful command references and common troubleshooting tips that can help if you run into issues. Before we move on, let's take a moment to quickly review some important Zephyr commands that we have used throughout this episode. This slide is meant to act as a quick reference, so you don't have to remember every command or rewind the video. You don't need to memorize this command. The goal is to know what they do and when to use them. Let's start with workspace and environment related commands. The command source.venv/bin/activate activates the Python virtual environment, which ensure all Zephyr tools use the correct Python setup. West init initialize the Zephyr workspace and West update downloads the Zephyr kernel and required modules. West Zephyr export configures the environment so the build system can locate the Zephyr source tree. Next are the build and run command. West build command builds a Zephyr application for specific board. West build -t run command runs the application using an emulator like a QEMU. West flash command flashes the application onto real hardware. Finally, for SDK management, we use West SDK install to install the Zephyr SDK and West SDK list to verify the installation. Before we wrap up this episode, let's talk about something very important, the troubleshooting safety net. If you are setting up Zephyr for first time, it's completely normal to run into the small issues. This slide is not about new concepts. It's here to help you recover quickly if something doesn't work as expected. One of the most common issues is related to the Python virtual environment. If the command like a West is not found, the first thing to check is whether the virtual environment is activated. Always make sure you see .venv in your terminal prompt before running Zephyr commands. Another common issue is related to Zephyr workspace. If West commands fail, make sure you are running them from the correct directory and that the workspace has been initialized properly. Commands like West init and West update must be run inside the workspace directory. Issues related to Zephyr SDK usually show up during the build step. If the build system cannot find a compiler or toolchain, verify that the SDK is installed using the West SDK list. When using West SDK install, Zephyr normally detects the SDK automatically, so manual environment variable setup is rarely needed. Another frequent source of errors is an incorrect board name. Always double check the board identifier you pass to West build. For example, QEMU x86 for emulation or STM32F429i disk 1 for the STM32 discovery board. If you encounter strange or inconsistent build errors, A clean rebuild often fixes the problem. You can do this by deleting the build directory or using pristine build. This forces Zephyr to regenerate all build files from scratch. The key takeaway here is not to panic when something goes wrong. Most Zephyr setup issues are environment related and can be fixed by checking just a few things. This troubleshooting slide is your safety net. Use it whenever you get stuck. With this safety net in place, you are well equipped to move forward confidently with Zephyr RTOS. In the next slides, we will wrap up this episode and talk about what's coming next in the series. Before we wrap up this episode, let's take a moment to recap what you have achieved. In this episode, you set up a complete Zephyr RTOS development environment on Linux. You installed all required system dependency using a single consolidated command, created a Python virtual environment, and used waits to manage the Zephyr workspace. You also installed the Zephyr SDK and successfully built and run your first Zephyr application. Most importantly, you saw the same application running both in QEMU and on real hardware using the STM32 F429i discovery board. This means your development environment is correctly set up and ready for real Zephyr development. Everything we cover next, thread, scheduling, drivers, and real-time behavior built on this foundation. In the next episode, we will talk through the Windows setup flow so you can follow regardless of your operating system. After that, we will start diving deeper into the Zephyr internals, including its architecture, threading model, and scheduling behavior. We will also begin exploring how drivers and devices are handled in Zephyr. If this video helped you, consider liking it and subscribing to the channel. And if you ran into any issues or have questions, feel free to leave a comment below. Thanks for watching, and I will see you in the next episode.